Assalamu alaikum. I'm going to discuss today flow control experiment, mainly the discussion part, how to generate the graph and how to interpret the result. Flow control experiment, as you know, that the objective is to find the ultimate gain and ultimate period by considering continuous cycling. So you will use these values, ultimate gain and ultimate period, to design a controller for the process. Process is flow control. So using Ziegler-Nicholas method and Tyrus-Lubin method, you will design a PID controller, PI and PID controller, using the value you got in the first step, that is finding the ultimate gain and ultimate period. Okay, so PID controller, you need a value of Kc, tau I and tau D. Okay, depends on each process. So where is your process? Your process is here, the flow control setup we have in lab. So this is the setup. Okay, so here we have the flow. You can see this closed circuit, water flowing and coming back to this tank. So here we have the controller, and this is a flow meter reading. It will read the flow rate. Okay, so you make a set point and change the setting of PID and see how much is the offset or how it is behaving. So for this one, you would use continuous cycling method to find, first of all, ultimate gain and ultimate period. How we move? If let's come to the procedure, experimental procedure. Ideally, you start with a small value of Kp or Kc. You know this with the name of proportional gain. This method says that, okay, if you start with a small value of Kc, initially, if you have only P controller, only P, and this is a set point, suppose. So you will have a small, you will have, wait a second, if this is a set point, you will have offset, right? So it will go like this. Now this difference is called steady state error or offset. So what you do, you keep increasing the value of proportional gain, Kp, and when you increase the gain, Kp value, you will see that the offset value, the difference between steady state value and the set point, the offset will decrease, but in doing so, it becomes oscillatory. Okay, oscillation starts. It becomes unstable. So you are looking for a value of Kp at which your oscillation is continuous. It means the amplitude is constant. Okay, so how this graph will look? The value of Kc at which your graph is like this. Okay, it means the amplitude value, they are almost constant. So this value of Kc at which this is happening, Kc or Kp, whatever, this is called ultimate gain, Kcu, U for ultimate. Okay, and those calculations suggested by Ziegler-Nicholas and TL, Tyrus-Lubin method, this is based on the value of Kc and Kcu, the value of Kcu, ultimate gain, and the Pu. What is Pu? Pu is the period, time period. It means the value of time, this is time, value of time between two peaks. So you read the time here and you read the time here, that gives you the Pu value. So once you calculate the Kc, U and Pu, you can get all the parameters for Pi, for PID, and then Pi and PID for TL and Zn. So one observation I want you to do right now, especially with the value of reset time tau I. This is integral time. For example, pi, Ziegler method says that it will be pu divided by 1.2, and TL method says that this will be 2.2 times pu. So in this case, we expect that tau I value will be higher than Ziegler-Nokolos method. Okay, same here for PID, pu divided by 2, and here we have pu 2.3, so it is like 1.1, 2.3 divided by 2. So okay, so this is also going to be more. So we'll discuss what's the effect of having higher tau I value or lower tau I value. Similarly, Kc values, here you can see 0.4, 0.6, and here 0.3, 0.45. It means that Kc value is low in TL method and high in Zn method. Okay, so now let's go to the experimental data we have. So for example, first of all, I will show you this one. This is the case when Kcu was 1.5. Kc was 1.5 or 1.1. This is 1.1, so it should be 1.1. Okay, so this is the data you can see is 1.1, the P control only when we run it, and this is the data, typical data. Okay, time, this is the set point 100 liter per hour. This is flow rate. X is the real variable. Okay, so this is, I have plotted this one. You can see from here to here with time. You can see this is almost continuous oscillation. So this is happening at Kc equals 1.1, so which becomes your ultimate gain. Now to get the ultimate period, you can read the time 4.6, x-axis is time 4.6 and 5.6, so around 1. So your pu is around 1 or 1.2, whatever. So based on this value pu and kcu, you can calculate the value of these parameters kc and tau I. Okay, now and then you run the system at those values. So for example, kcu was 1.1 something, so you get the kc and tau I. You can get ready with this table and then run the system at those value of pi parameter or PID parameters. So now I will go to the data. Okay, so for example, here we have data for, this is PITL method. So you can see that tau n is 1.6, which is a little bit higher than Zn. We'll see that. Okay, so Kp is this and tau I is this, is tau I basically. So you can see this is the data time, this set point. So 100 and 100, the almost set point and real variable are the same, and here we give the set point change, so 100 to 150. So if you want to plot, you can plot from here, and it's taking some time to reach the set point. Now it's reached the set point. Okay, so if you plot this one, this is real variable, real flow rate. Okay, and this is the time. You can see the graph. Where is the graph? This is the graph. So I need to adjust the axis. Okay, so I have adjusted the x-axis, so now it looks better. So how to explain this graph? Set point was 100, this is flow rate, and then the set point is changed to 150, as you can see in data as 100, and then it's here we change the to 150, and then the real flow rate also started changing. You can see it's very fast up to 140, and then it is going slower. So you can see here it is going, and then how to explain this? Is there any overshoot? No, because it is not going beyond the set point. It is reaching here and then almost coming back, and then again reaching to the set point almost now here. So you can say that this taking too much time, or it has sluggish response or slower response. Okay, so this is a PI method. The value of Kp tau I, this is tau integral time, is calculated by TL method. Okay, so this is what we get in PI. Then we will compare the same performance of PI with that of ZN method. So what about when we have Ziegler method? So I will go to the another Excel sheet, this one, and this is PI ZN. Okay, the values are Kp and tau n, and you can see here the set point is 100. Then we change the set point from 100 to 150, and you can see that changes started. It is going beyond the set point. You can see 150. So here we expect that we will get overshoot, and then coming back to the set point. You can see I have plotted now both of them. Okay, that from ZN and TL to compare. So this is the one with ZN method. So you can see it is going faster, but it has overshoot. It's going beyond the set point, almost 160. Set point, new set point is 150. Okay, then coming back, but it is reaching the steady state faster. So what's the major difference between ZN and TL? And this is the TL. TL is, as it approaches to the set point, it becomes overcautious. It doesn't want to oscillate or overshoot, and then it's almost decreases. Okay, and then again slowly going to the set point. So it means that the TL method is slower dynamics wise. It will not have any oscillation, it will not have overshoot. In the other side, Ziegler method may have oscillation or may have overshoot, but it will be faster. So this is all about the comparison between this. So let's see the numbers. This is the number of TL. So I will put it together to compare. This is ZN and this is TL. So you can see Kp is almost same. Depends on, like, ideally should be for TL should be less. Okay, but we have experimental data from maybe different group, that's why. But the major difference is Tn. The integral time for Zn is 0.5 and for TL is 1.6. So higher the value of integral time, the slower the response will be. This is, as you know, that integral time work as inverse of 1 over tau I. So if the 1 over tau I, so in this case Ziegler 0.5. Okay, so this is 2, and for TL 1 over 6. So this is this number is higher. So we expect here the response will be faster, aggressive. Okay, so this is comparison of TL method and GN. I expect you to do the same analysis for PID, Ziegler, PID TL. Try to plot like this on the same graph to compare. Okay, and we have one more thing. Yes, what about disturbance? So if you create the disturbance and in the system, not the set point change, so you can see set point is 150. This is the real variable, and we are running at those values kp, tau n, and tau d. This is PID. Okay, we want to check how this PID setting is working with the disturbance. So this Z is basically disturbance in the system we can create by changing the value of Z. So right now it is 0, all set. Right now there is no change. So you can see here we make it 10. So here you are trying to create a disturbance in the system, and now the value will change. Controller will act and try to reject this disturbance and put it back, bring back to the set point. So if you plot this one, okay, versus time, okay, and see I need to add time, then let's see. Okay, where is the graph? $150 and okay, let me draw like, also I need to add so this was the immediate drop, and then it is coming back to the set point. I need to add more data point just to, okay, so from here, so that we know that it came back. Yeah, again up to here. You can see this is again as disturbance. So now you can see this graph. So immediate drop because of this disturbance, and then it is coming back to the set point. So it is rejecting the disturbance, and it is taking some time to put it back to the set point. So this is the one data you have, and you can analyze, you can put it and make the table, make the graph. This is for disturbance for the PID setting. Okay, so that's it. You can summarize your all the results with this. This is the picture from your book, control book. So you can see this is the study with respect to the Kc. Kc is increasing in this way from 1 to 3, 5, and tau I is increasing this. This is for disturbance. So 0 is the set point, and then it's, so as you increase the Kc, oscillation increases. As you increase the tau I, oscillation decreases. Okay, and this is with respect to the disturbance. For the set point change, you can see, so set point change is here, Kc is increasing, Kc increases, becomes oscillatory. Tau I is increasing in this way, so as you increase the tau I, the integral time oscillation decreases. Okay, Kc value is less, also this is slower. So if you compare this and this, tau I is the same, but Kc is smaller. Kc is smaller in this way. So this is oscillation is less. Now with higher value of tau I, it becomes less oscillatory as well as become very slow. So this, you can see this graph, last graph, it is taking more time, is overcautious, is sluggish, slow in dynamics. So it is taking more time in reaching the steady state. So higher value of tau I, as you have seen, higher value of tau I in TL than Gn. That's why TL method is slower than Gn. Okay, so that's the summary of the results and analysis. Hope it's clear. You can come back to me by any questions. Okay, thank you.